Ever wonder how a skyscraper can ride out an earthquake? Or how an airplane wing can flex like crazy in turbulence but never ever snap? Well, today we're going to dive into the predictive power that lets engineers literally see the future, to find a material's breaking point long before it's even built. It's how they design a world that, quite simply, doesn't fall apart. It really all boils down to one big question. How can you be absolutely sure something is strong enough before you build it? The answer, it turns out, is this fascinating mix of physics, supercomputation, and now artificial intelligence. It's the invisible engineering that underpins everything from the truly massive, like these giant earth dams, right? Where engineers have to calculate the immense, relentless pressure of all that water to prevent a total disaster. All the way down to the tiny, intricate world of mechanical gears, where every single tooth has to handle constant friction and force without chipping or failing. And even to things like custom surgical implants, which have to be tough enough to work perfectly inside the human body for an entire lifetime. Every single one of these things, from the super simple to the incredibly complex, they all rely on one thing: the ability to predict their own breaking point. And this ability, this power to predict failure, that's the fundamental challenge engineers have been wrestling with for decades. I mean, you can't just eyeball a steel beam and see its internal weaknesses, right? Engineers need a way to make these invisible forces visible. They need to map out the stress and the strain and pinpoint the exact spot where a catastrophic crack might start. So, for years, the go-to tool for this has been this incredibly powerful digital simulation technique. You can think of it as the classic toolkit. It's called finite element analysis, or just FEA for short, and the core idea is actually brilliantly simple. You take something impossibly complex, like a car chassis or a whole plane wing, and you digitally slice it into millions of tiny, simple, manageable pieces. They're called elements. If you can solve the physics for each tiny piece, you can understand how the whole thing is going to behave. So the process kind of looks like this. First, you've got your 3D design. Then the software creates this intricate digital mesh, breaking it down into all those simple little shapes. After that, you get to have fun. You apply virtual forces. You push it, you pull it, you twist it, and the computer calculates the result for every single one of those elements. And the final result? It's this beautiful, color-coded map that shows you exactly where the stress is highest. Red means danger, blue means you're totally safe. And because it's so versatile, FEA is used absolutely everywhere. Researchers use it to make sure dams are stable, to see how well adhesives are going to hold up, to find the exact fracture point in a critical bolt, to design lighter and stronger bicycle frames, and even to model how a jaw implant will actually fuse with your bone. It's really become the universal language of structural strength. But as powerful as FEA is, it does have its limits. It can be super slow, and it needs a ton of computing power. And that's where we start to see a really intelligent upgrade. This is where artificial intelligence steps into the picture. See, classic FEA is purely physics-based. It just crunches numbers based on the laws of mechanics. But AI hybrid models, they do that too, but they also learn from massive amounts of data. Think of it like an experienced engineer who's seen thousands of designs succeed or fail. The AI starts to develop an intuition. It finds patterns and shortcuts that a purely physics-based calculation might miss, which gives us predictions that are not just accurate, but way, way faster. And what's really crucial here is that these new hybrid models aren't replacing the old methods. Not at all. They're making them better. They fuse the proven physics of FEA with the incredible pattern recognition of AI to create something way more robust. And what this allows engineers to do is, well, it's pretty profound. The AI can connect the dots across totally different scales. It can look at information about tiny atomic-level defects in a material and predict how those microscopic flaws are going to affect the overall strength of a full-sized bridge. It's the complete picture of performance. So what does all this advanced modeling actually mean for us in the real world? Okay, let's talk about the payoff. The benefits are incredibly concrete. In biomechanics, for instance, these models help design implants that actually mimic bone better and help us heal faster. For advanced composites, they can predict exactly how tossing in some nanoparticles will boost strength. And in alloy design, an AI can tweak the recipe for a metal to get that perfect sweet spot between strength and rust resistance. And the breakthroughs are just popping up all over the place. We're seeing stronger bolted joints for cars and airplanes. We're getting more reliable manufacturing processes. Engineers are even figuring out how to use natural fibers, like from chicken feathers and sawdust, to create new lightweight and strong materials. And they're designing smart materials like shape memory alloys with unbelievable precision. So all of this is pointing to a future where we don't just test materials, we can truly predict and design their performance right from the atomic level all the way up. And this quote really just nails it. This isn't about physics versus data anymore. The future is the synergy. It's about combining our deep understanding of the physical world with the incredible pattern spotting power of AI. The result is a framework that's just smarter, faster, and more reliable than anything we've had before. Which it kind of leaves us with this one fascinating final thought. For centuries, engineering has been about managing risk, building in these huge safety margins just in case. But as our ability to predict failure gets closer and closer to perfect, when we become almost certain of how things will behave, what new, more efficient, more ambitious things will we finally dare to build next?